Sometimes the simplest questions have the most amazing answers. Like, how can trees be so tall? It's a question that doesn't even seem like it needs an answer. Trees just are tall. Some of them are over 100 meters. Why should there be a height limit? I'll tell you why. Trees need to transport water from their roots up until their topmost branches in order to survive. And that is no trivial task. There is a limit to the height that water can be sucked up a tube. It's 10 meters. If you suck on a long vertical straw, the water will go no higher than 10 meters. At this point, there will be a perfect vacuum at the top of the straw, and the water will start to boil spontaneously. For a tree to raise water 100 meters, it would have to create a pressure difference of 10 atmospheres. How would trees do that? When I posed this conundrum, a lot of people said the answer is transpiration. And that's when water evaporates from the leaf, pulling up the water molecules behind it. Now that's clearly a mechanism a tree can use to create suction, but it doesn't help us overcome this 10-meter limit.
The lowest the pressure can go is a pure vacuum, which I imagine is not happening inside of tree leaves. Right?
Right, Hank. So you might suspect that a tree does not contain continuous straw-like tubes.
The tree effectively has valves in it, so you don't have a column of water.
This big tube, which you're saying needs to be filled with water, is actually made up of cells.
Although these are good speculations, they don't turn out to be correct. Scientists who study trees find that the xylem tubes that transport water do contain a continuous water column. So how else could the tree transport water from the roots to the leaves?
They don't suck. They don't use a vacuum.
Okay, so how do they do it?
Squeezing like a cow, like you're squeezing a cow udder all the way up. There's little tree muscles in there.
Yeah. Besides being a giant waste of energy, all of the cells that make up the xylem tubes are dead. What about osmotic pressure? If there is more solute in the roots than in the surrounding soil, water would be pushed up the tree. But some trees live in mangroves where the water is so salty that osmotic pressure actually acts in the other direction, so the tree needs additional pressure to suck water into the tree. Then it must be capillary action. The thinner the tube, the higher the water can climb. But the tubes in a tree are too wide. At 20 to 200 micrometers in diameter, water should rise less than a meter. So how do trees do it? Well, one of the assumptions we made is wrong.
The lowest the pressure can go is a pure vacuum. Pure vacuum. Pure vacuum.
In a gas, this is true. When you eliminate all of the gas molecules, the pressure is zero and you have a perfect vacuum. But in a liquid, you can go lower than zero pressure and actually get negative pressures. In a solid, we would think of this as tension. This means that the molecules are pulling on each other and their surroundings. As the water evaporates from the pores of the cell wall, they create immense negative pressures of minus 15 atmospheres in an average tree. Think about the air-water interface at the pore. There is 1 atmosphere of pressure pushing in and negative 15 atmospheres of suction on the other side. So why doesn't the meniscus break? Because the pores are tiny, only 2 to 5 nanometers in diameter. At this scale, water's high surface tension ensures the air-water boundary can withstand huge pressures without caving. As you move down the tree, the pressure increases up to atmospheric at the roots. So you can have a large pressure difference between the top and the bottom of the tree because the pressure at the top is so negative. But hang on, if the pressure at the top is negative 15 atmospheres, shouldn't the water be boiling? Yes, it should. But changing phase from liquid to gas requires activation energy, and that can come in the form of a nucleation site, like a tiny air bubble. That's why it's so important that the xylem tubes contain no air bubbles, and they can do this because unlike a straw, they've been water-filled from the start. This way, water remains in the metastable liquid state when it really should be boiling. It's just like supercooled water remains liquid even though it should be ice. So you could say that the water in a tree is supersucked because it remains liquid at such negative pressures. And why are trees moving all this water up the tree? I want you to make a guess. Say it out loud. For photosynthesis? Actually, no. Less than 1% of the water is used in photosynthetic reactions. Any other ideas? Okay, what about growth? Well, 5% of the water is used to make new cells. Well, so what happens to the other 95% of the water? It just evaporates. For each molecule of carbon dioxide that a tree takes in, it loses hundreds of molecules of water. Whoa. Can you believe how amazing this is? Trees create huge negative pressures of tens of atmospheres by evaporating water through nanoscale pores, sucking water up 100 meters in a state where it should be boiling but can't because the perfect xylem tubes contain no air bubbles, just so that most of it can evaporate in the process of absorbing a couple molecules of carbon dioxide. I will never look at trees the same way again.
They don't really eat anything.
How does that make any sense?
They don't eat anything. No, they don't eat anything. Water is all they absorb.
I'd like to say a huge thank you to Hank, Henry, and Professor Polyakov for making on-camera hypotheses. This is an essential part of the scientific process, even if your hypothesis turns out to be wrong. As Einstein said, a person who's never made a mistake has never tried anything new.
I've always wondered what it would be like to be on this side of
You can get
Veritasium video.
Now, I'd be surprised if you weren't already subscribed to these guys, but if you're not, go click on these annotations and check out their channels, and you may just learn something. I'd also like to thank Professor John Sperry from the University of Utah. He walked me through all of this in an hour-long Skype conversation, so I'm going to put a link to his website in the description. We're looking at pressures here below atmospheric, is that right?
That's right, below atmospheric. This is liquid pressure, not gas pressure. So it's a common misconception that, oh, you can't have, negative pressures because there's no molecules left. The definition of pure vacuum is 0 molecules. That's for gas, okay? So just to be clear,
I think this was one of my big problems in understanding this. This video would have been impossible without CGP Grey. When I told him about this idea in London,
and I felt like mind just blown with this whole thing.
He said it was going to be really hard to explain, and when he says it's hard to explain, things are going to be tough. So thank you for all your input to this script. And thank you for watching. Making this video has been a real odyssey for me, so thank you for joining me on that journey. I really appreciate all of your comments. And if you haven't subscribed to the channel already, you can click the annotation or click the link above and join me on my next scientific adventure. I made a video promising to make a video about the answer to this. I proposed the problem a couple months ago, and I was like, subscribe to the channel, I'll give you the answer next week.
You have to go
the
to
lies.
Drive it at the right frequency.
Yes! Success is frightening.